Today I'm here with lecture 3, right? Lecture 3 of chapter 2, right? Chapter 2. Today I'm going to find, first I'm going to find electric potential due to thin spherical cell, right? Electric potential due to thin spherical cell, right? In chapter 1, right? I calculated electric field due to thin spherical cell, right? Okay. So in this one we are going to calculate potential due to thin spherical cell. Okay, so I'm writing here electric potential due to thin spherical cell. Okay, due to thin spherical cell. Okay, this is your spherical cell, right? And this spherical cell is having radius R, okay, and charge on this thin sphere is how much? Q, right? And how much electric potential this one is creating, that one we are going to calculate, right? So now I am writing it. Let us consider a thin spherical cell having charge Q and radius R. Okay, calculate what we have to find. Calculate electric field, right? Electric potential. Calculate electric potential. Calculate electric potential at a point. First one, at a point outside the sphere, right? At a point outside the surface. At point outside the surface, right? At a point outside the surface, right? So point is outside. That means a small r will be greater than your capital R, right? And similarly, at surface and surface R is equal to R. And third one, inside the surface, right? Inside the surface, that means a small r is smaller than capital R, right? So first I am going to calculate outside the surface, right? Now I am writing here outside the surface. So outside the surface, small r is greater than capital R, right? Now suppose this one is a cell, right? Now point I am taking outside. Yes. So suppose this is your point. At this point we are going to find electric field, right? At this point, right? And this point is located at how much distance? This point is located at r distance, right? Or we can write position vector of this point with respect to center is r vector, right? And now one more thing, what is the direction of electric field at that point? That things I already calculated in chapter 1, right? And direction of electric field is like this, right? So electric field is in this direction, right? Now we have to find potential at this point. Suppose this is your point P. Okay, at point P we have to find electric potential, right? That P is outside. Okay, now yesterday I wrote one formula. Have you remembered that? This one, V final minus V initial. V final minus V initial is minus of dot dr. I hope you remember it. Okay, so this is your formula, right? So why I am writing this formula? Because with the help of this formula I am going to calculate electric potential outside the spherical cell. Okay, now suppose I am bringing a unit positive charge. Suppose I am bringing a unit positive charge from infinity to this point, infinity to this point, right? That means initial position was at infinity, right? Okay, in first lecture, right, you wrote the definition of electric potential, right? So electric potential is defined as amount of work done required to bring in unique positive charge from infinity to that point, right? Suppose I am bringing a unique positive charge from infinity to this point, right? So initial point is at infinity, yes or no? So we can write now from this formula, we can write Vp. Vp is your final point. This is your final point, right? And initially infinity, yes or no? Yes. And now minus integration of E dot dr, and initial position was this much. So lower limit will be at infinity and upper limit will be P. And how much is the distance of P? R. Right. Now you can see here electric field as well as dr, both is along same direction, right? R is along this direction, right? So R is dr is what? A small change in R, that will also coming along the direction of R, right? So angle between, see, your R and E both is along same direction, yes or no, right? And dr is what? A small change in R, right? So that dr is also in direction of electric field, right? That means angle between these two is 0, right? Both is along same direction, so angle will be 0. Okay, so angle is 0. So further we can write here infinity to R E dr cos 0. Cos 0, right? Cos 0 is 1, right? Now see, further I am writing like this. Okay, again in chapter 1 you calculated electric field outside. What was the formula for electric field? This one is the formula. Electric field outside a thin spherical shell is kq by r square, right? Kq by r square. So you know this one, I already calculated it your previous chapter, right? So this is this one, right? So we have to substitute value of this one here, right? So kq by r square, here minus will come, okay? Kq by r square, lower limit is upper limit, and dr cos 0 is 1, so I am not writing that, okay? So now, so kq is constant, so that comes out, okay? So what value we have inside? We have dr by r square, right? Lower limit is infinity to r. You are able to integrate this value. So after integration, you are going to get minus q minus 1 by, and this value is r to infinity, right? See, 2 minus is here, so we can cancel it, okay? So finally I am writing kq by r, kq 1 by r minus 1 by infinity, right? 1 by infinity is how much? 0, right? So finally what value is coming? After this I am writing here in a small box, okay? So what value? Vp minus v infinity, right? Vp minus v infinity is coming 1 by infinity is 0, right? So kq by r, right? Now one more thing, at infinity potential is 0, right? At infinity potential is 0, right? So finally we can write Vp is equal to kq by r. So this is your formula to calculate electric potential outside a thin spherical shell, right? So kq by r, just you have to remember this formula. So next I am going to discuss at the surface, right? At the surface. So space. So now I am going to run this part because the space is not available on blackboard now, right? So I have to erase it. Okay, now B at surface, right? At surface, at surface, a small r is equal to capital R. Yes or no? Right? A small r is equal to capital R. Okay. So formula will be kq by r. This is formula, right? Okay. And now last one. Last one is inside the surface, right? Now I'm going to find inside the surface. See, inside the surface. Inside the surface R is okay. Inside the surface. Again we are going to use same this formula, okay? This one we are going to use. Calculate inside the surface. Okay. Suppose this is your thin spherical shape. Okay, I'm trying to draw a little bit bigger, okay? This is your thin spherical shape, right? What value is known? At surface potential is known to you, right? This is your potential at surface. This value is known to you, right? So what I am doing here? I am taking a charge, unit positive charge, right? It's taking a unit positive charge from this to this. See, at this point we have to find potential, right? This point is located at how much distance? This point is located at r distance from the center of a sphere, right? Now, potential at surface is known to us, yes or no? This much, right? And now, further we can write, suppose I'm taking unit positive charge from here to here, right? Here to here. Suppose this is your P, this is your S. Okay, so after that we can write here V final minus initial. Final is your S, right? Final is your S minus V initial. P is your initial, V final minus V initial. V final is this one, initial is this one, right? Is equal to integration of E dot dr, right? And E dot dr is how much? E dr. Right, and how much is the value of R? How R is changing? R here, value of R is, and here is smaller, right? Now, have you remembered electric field inside a thin spherical shell is 0? Yes or no? So this value of E is 0, right? And what is this value? This value is not. This is your point P, which is at surface, right? And how much? KQ by. So we can write ds minus kq by r, and here r to r, 0 into dr, value will be 0, right? So final what formula is coming? Vs is equal to Vs minus kq by r is equal to 0, right? Yes or no? So after this you are able to write, after this I am writing here. So Vs is equal to kq by r. As you see, Vs kq by r. Q is charge on the sphere, r is the radius of a sphere, and k is the electrostatics force constant, right? That means all term is constant, right? That means electric potential inside a thin spherical shell is constant, right? That one is not changing, okay? And that constant value is how much? Kq by r, right? Okay. So now I'm going to rub this part, okay? Now I'm going to draw graph, right? Graph of V versus R. Graph of V versus R. Graph of V versus R, okay? V is potential, R is the distance from the center, right? Now, so see, suppose at this point R is becomes equals to R, right? So all the point which is lying in this region, right? All the point which is lying in this region, for the point which is lying in this region, r, small r is smaller than capital R, right? That means potential is constant, right? Potential is constant, and that potential is how much? Kq by r. So on this axis I am taking potential now. On this axis I am taking potential, right? So V is taking on this axis. So suppose this is this point, right? Okay. Now here to here potential is constant, and that value is how much? Kq by r, right? You are able to see it. And after that formula was this one. V is equal to Kq by r. That means beyond the surface, right? Potential is decreasing with R. Here you can see now B is inversely proportional to R, right? So in this region potential is decreasing with R, right? So this is your graph for potential and R, right? Where R is the distance from the center, right? And in this region R is greater than capital R, okay? So this is all about your electric potential due to thin spherical shell. Okay, so I hope everything is clear to you, right? So next I am going to discuss equipotential surface, right? Equipotential surface. Equipotential surface, right? So this is clear from the name, right? A potential having equal potential is known as equipotential, right? Eq means equal, right? Potential surface, right? So a surface, definition will be a surface having equal potential, a surface having equal potential, okay, at all the point on the surface is known as, right, a surface having equal potential at all the point on the surface is known as equipotential surface, right? Next I am going to write property of equipotential surface, right? So properties of equipotential surface, right? So first point, okay, you can see potential is equal at all the point of the surface, right? So first point is electric field, right? Electric field and electric field lines, okay? Electric field and electric field lines is always perpendicular to equipotential surface, right? Okay, so now I'm writing electric field or electric field lines always perpendicular to equipotential surface, right? Perpendicular to equipotential surface. Electric field or electric field lines always perpendicular to equipotential surface, right? How you are going to believe it or not? No, you are not going to believe it, right? So I have to do something to make you believe, okay? So now you can see, suppose this is a point charge, okay? Point charge, right? Point charge, okay? So point charge, you know the formula to calculate electric potential due to point charge, right? What was the formula? KQ by R, yes or no? What was the formula? KQ by R. This is KQ by R is electric potential due to point charge, right? That means from this formula, these two terms is constant, right? If R is constant, right, then potential will be constant, right? So if you are going to fix R, then you are going to get a sphere, right? See all the point which is lying at R distance, all the point which is lying at R distance from center, all the point which is lying at R distance from the center, right? Potential will be 0. From this formula you can see all the point which is lying at R distance from the center, potential will be same, right? And that potential is how much? KQR. And what is the shape of this one? It will come in a spherical shape, right? Okay. Now, so one thing is now clear. At all the point on this surface, potential is equal, right? So this is your equipotential surface due to point charge, right? So one more thing you have to remember. Due to point charge, equipotential surface is concentric sphere. Yes or no? See, now you are able to draw more sphere like this. So all these are equipotential surface at all these point on the surface is same. Potential at all these point on the surface is same. Similarly this one. So for point charge, equipotential surface will be concentric sphere, right? Whose center is lies on the charge. Okay. Now, so one thing is clear, right? For point charge, equipotential surface. This is your equipotential surface, right? Yes or no, right? And one more things I discussed. This is point charge, and this point charge is positive, right? So electric field lines will originate, right? So electric field lines will originate like this. Now you can see clearly this electric field lines is perpendicular to your surface. Yes or no? This electric field lines is perpendicular to your surface, right? Perpendicular to your surface. So electric field lines is along the direction of electric field, right? So electric field is also perpendicular to surface, right? So somehow with this example we are able to see that electric field lines is perpendicular to equipotential surface, right? I taken this one as an example, right? But this is true for all the surface, right? Okay, so next point now I'm going to write point number 2. Point number 2, right? What is that? Work done in moving a charge, right? So work done in moving a charge Q on equipotential surface will be 0. Work done in moving a charge Q on equipotential surface will be 0, right? Why this one is becoming 0? Oh, again you are not going to believe me, right? So I have to show you something, okay? In last class I gave you one formula. What was that formula? V final minus V initial. V final minus V initial is work done by Q. W is your work done. Yes or no? Right now we are talking about equipotential surface, right? And I am moving the charge on equipotential surface, right? And equipotential surface is a surface having equal potential, right? That means your final is equal to initial, right? Equipotential surface, that means potential at all the point of the surface is same, right? I am moving the charge on the equipotential surface, right? That means your final potential is equal to initial, right? That means suppose final is V, initial is also V, right? So you can see V minus V is 0. So W is also 0, right? And W is work done in moving charge, right? Okay. So many point is also possible, but other point is also somehow related from all these points, okay? So that's why I'm not going to discuss more points. So just write only these 2 points regarding your property of equipotential surface, right? Okay, so next I'm going to discuss electric potential energy, okay? Electric potential energy, okay? So electric potential energy, okay? Electric potential energy is represented by U, right? Electric potential energy, right? So first I'm going to write definition of electric potential energy, right? So I have to write definition, okay? So in electric field, electric potential in electric field, electric potential energy, right? Electric potential energy of a charge at a point of a charge at a point is defined as the work done, defined as the work done in taking the charge from a reference point from a reference point in bracket, right? Reference point is generally taken as infinity, right? Generally taken at infinity, right? Generally taken at infinity to that point, right? So in electric potential energy of a charge at a point is defined as the work done in taking the charge from a reference point to that point. Okay, suppose this is your point, right? At this point I am bringing a charge q, right? And this point is located at in electric field, right? Suppose this is your electric field, okay? Located in electric field, right? Suppose this is your electric field. I am trying to show you electric field, okay? So electric field is electricity. These are the electric field lines, huh? So electric field lines is present, that means this point is in electric field, right? So suppose I'm bringing this charge q at this point, right? I'm bringing this charge q at this point, right? From infinity, right? And from infinity, right? From infinity to this point, right? And in bringing, I'm doing how much work? How much work I'm doing? W external, right? So potential energy will be, right? You will be your potential energy, right? W external will be potential energy, right? Because see now, this amount of work done is required, right? In bringing charge q at this point, right? And that work done is equal to your potential energy, right? Okay. So this is your this way we are able to calculate electric potential energy, right? So to find electric potential energy, we have to find work done, right? And if I am able to calculate work done, that work done is equal to potential energy, right? So next I am going to calculate electric potential energy due to point charge, right? Electric potential energy due to 2-point charge, right? Due to 2-point charge, okay? Oh, sorry. Before that, I have to discuss unit and all those things, no? Right? So you have to write some points regarding this one, right? I hope you written this part, okay? So now I'm going to wrap this part. So note, okay? So first I'm going to talk about unit, right? What is the unit of potential energy, right? So first point is unit of potential energy, okay? Unit of potential energy, right? So energy unit will be joule, right? So unit will be joule, right? Okay, unit will be joule, okay? And one more unit is also possible, right? What is that? Or volt per coulomb. This is volt per coulomb, okay? Volt coulomb, right? So only these two units of potential energy is possible, right? And whatever it is a scalar or vector, it is a scalar quantity. Energy is a scalar quantity, right? So second point you can write, it is a scalar quantity, okay? It is a scalar quantity. Okay, finish. So electric potential energy of 2-point charge, right? Electric potential energy of 2-point charge. Electric potential energy of 2-point charge, right? So this is one charge, right? And another charge is present here, right? And this separation is how much? This separation is R, right? And we are going to find potential energy of these two charge system, right? Yes or no?
Yes.
Okay. 2-point charge system, okay? Electric potential energy of 2-point charge. I'm going to define electric potential energy of this point charge at this point, right? And that will be the potential energy of 2-point charge system, right? So first I have to calculate work done. How much is work done required to bringing this charge here, right? Okay. So suppose I'm bringing this charge from infinity, right? Infinity to this point, right? So as I am bringing from infinity to this point, right? As I am bringing from infinity to this point, right? At some time, it will be at x distance from this point, right? Yes or no? And at x distance, how much force is acting? At x distance, how much force is acting? Force is acting on this one, right? And that force is how much? That force is Q by x squared. Yes or no? This much force is acting on this charge at x distance, right? This is intermediate state, right? Yes or no? See now these two charges separated by how much distance? This much distance, right? So force will be KQ x square, right? This amount of force will act, right? And now a small work done in a small distance. Suppose I am displacing this one by very small distance dx, right? A small distance dx, right? So we can write here. So now I am writing here electric force on charge Q at suppose this point is P, right? At point P is how much? At point P is F, and F is how much? Q by x square, right? Okay. So now I am displacing this one very small distance. That small distance is dx, right? So now a small work done by electric field. A small work done by electric field, right? And a small work done is dw, and that dw is F into dx, right? So now we calculated a small work done, right? Due to electric field, right? Okay. So similarly we can write here total work done, right? Total work done by electric field. Total work done by electric field, right? Total work done by electric field is W, and that W is integration of this quantity, right? F dx, and lower limit is infinity, right? And upper limit is R. At this point I bring the charge. Yes or no? Now value of F is known to you, right? Your F is equal to KQ by this much, right? So now I'm going to, so you are able to understand limit, how I am substituting the limit, right? Initially this charge was at infinity, right? And now I am bringing this charge at this point, right? And how much work is done? That work is potential energy, right? So basically we are going to calculate work done, right? Okay. So now I am going to rub this part, okay? So you can see here F is this much, right? So F is equal to integration of minus infinity to R, right? And this is Q by x square dx Q, right? And this is how much? Dx by x square, right? Infinity to R. Again Q by this quantity, integration of this one will be how much? Minus of 1 by x R to infinity, right? R to infinity. Here a square will come, okay? So and now further we can write minus KQ. Suppose I am taking minus out, okay? So KQ, and inside the bracket what value will come? 1 by R minus 1 by infinity. 1 by infinity is 0, right? So what value is coming? KQ by R. KQ by R. This much is coming, right? So this is, and 1 minus will also come. So this is work done by electric field, right? Yes or no, right? So now work done by external is what is work work done by external is equal to minus of work done by electric field, right? And minus of work done by electric field is how much? Minus kq by r. This minus becomes plus. So work done by external is how much coming? kq by r, right? So this is work done by external, and work done by external is your potential energy, right? So next we can write here. I have to rub this part. Okay. So now we can write by definition of electric potential energy. Electric potential energy is equal to W external, right? And W external is how much? kq by r. So this is your formula to calculate potential due to 2-point charge. Okay. So that's all for today. So in next class I will try to finish your potential energy. Okay. So that's all for today.